Okay, so this time I want to talk about my recent obsession, which is with open dynamical systems. So, this is something that category theory has been developed for over the last few years, and I think it's a tremendously exciting kind of area where we can use some diagrams to describe these very general sorts of systems which can have inner dynamics, but they can also receive signals from outside and produce signals that can be sent elsewhere. So we can think of these as little boxes that we can wire together to make larger open dynamical systems. And then there are some amazing extra developments which allow us to make these systems where the wiring patterns change. And also, I've recently had some extra ideas about how we can maybe go even further and we can have these open dynamical systems perhaps self replicating. So maybe we can model some things in biology, for example. So I hope you'll enjoy this content. It should be very easy to follow. I'm not going to be requiring many high level abstractions. It's going to be very sort of visual. And we're also going to learn some things about lenses along the way. So let's start then with the idea of an open dynamical system. Now, there's a more general definition, but I'm going to work in a pretty simplistic way. So I'm going to say that we can take inputs and those, let's say they're values in a set. So we have this set B minus with possible inputs. And we've got our system, and this system has a state. Okay. So you could think of yourself. So you could think of yourself as an example of one of these open dynamical systems. The state might be the inner state of your body, for example, or whatever goes on inside us to kind of make us who we are. And then what we have is an update function. And what that does is it takes in our current state, which will go in here, and also this input that we're receiving from the outer environment, and then it produces a new state. So that's how our update map works. And so we have this new state, and then we have this sort of feedback loop. I'll explain that in a minute. And also, we can produce an output. So that's going to allow us to take our inner state and produce some kind of output that takes a value in this set. So these things together constitute our open dynamical system. So that's what it is. We could write this as capital F. We could also write it, I'm introducing a bit of notation here. I'll go over this in more detail later, but we could also write it as F sharp F. So I'll get into that later. But really, the point here, and this is very important because suddenly I've introduced all of this, all of these pictures, and you can see in this picture it's quite involved in a way. You know, we've got feedback loops. What does that mean? Are things going back in time? We've got this. Is this a copy? It kind of is, but honestly, in a sense, the details of this picture don't matter. What really matters is that this open dynamical system just involves 5 pieces of information. We have this set of internal states. We have this set of possible inputs, B minus. We have this set of possible outputs, B plus. And then we have 2 functions. So we have this update function that's going to take a state and an input, and then it's going to give us state. And we also have this readout function, and that's going to take our state and it's going to produce an output. So really, you could see all of this picture as just a fancy way of encoding that we just have these 2 functions. So, okay, that's what an open dynamical system is for us. It's also known as a Moore machine, also known as a stream transducer. And what's interesting is the way that we think about this, because what we think about is that there may be a stream or a infinite sequence of different values flowing in on this wire from the left-hand side. So the system, we can think of it as receiving this sort of stream of inputs, and the system would start in a particular internal state. So a internal state that would be a value in this set of states. And then what happens is that on the next time step, the state of our system is obtained by updating it using this function. So we look at what the current internal state of the system is and the current input that it receives from the outside world flowing in along this wire, and that gives us the new internal state of the system. And also, this system is going to produce a stream of outputs. So the output it produces at time t is going to be obtained by doing this readout map on the current state. So this is the basic idea, and I think this is already an enormously powerful idea, especially when you think of it in terms of these kind of pictures. And hopefully you can see at least the sort of intuitive logic behind this sort of picture, right? That the system's receiving this kind of stream of inputs. It's in a particular internal state, and then using this internal state, we can sort of update the internal state also using this input. And then we're going to get, as the internal state is changing, we get this stream of outputs coming out. That's why it's called a stream transducer. So there are millions of examples of things we can think of as these open dynamical systems. Like you, for example, can be modeled this way, right? You have an internal state of your body. You receive information from the outside world. For example, now your ears are receiving these sounds coming from your computer, and then that's influencing how, for example, your brain state is changing. So, based on the current brain state and the stimuli that you're receiving, you'll get a new brain state. And then maybe you're doing something like talking or writing or something, and that's using the internal state of your body to produce a stream of output information. And your computer, similarly, it also has an internal state, and you type things on the keyboard, you're giving it inputs, and then based on what's going on inside the computer, you're going to get information coming out. So a lovely thing about this sort of graphical language, I mean, there is a formalism behind it. I'll mention some of the ideas, but you can already see that the idea of wiring together these open dynamical systems seems to make sense. And it's a very lovely way to think. So for example, we might have keys that are being pressed on a keyboard, and then these are sort of flowing in, and then we've got a kind of update function, and this is updating the memory in our computer. And so the way that the computer's internal state, which I shall call memory, is updated, it depends on its current state of its memory and also the keys that are pressed to influence it. And then we can do a sort of visualization of some of the aspects of what's inside the computer. And this goes to the monitor. Now so we could sort of think of the computer, at least a very simple model of it, like this. But we might also have a user, and that user can see what's going on in the monitor, and then they'll also have an internal state. Maybe that's the state of their brain or their body, or I don't think people have really worked out exactly what should be regarded as the set of internal states of people, but at least we can think of it as a toy model, right? So then based on the current state of the person and what kind of visualized stimuli they're receiving, their internal state is going to get updated. And then based on what they see, they might press some keys. So we could have something like this. And then we can box this off. And so we can box this off. This would be our user. And then if we have someone who's always using a computer, then we can think about the system as being wired together like this. So, you know, the computer gets the keys pressed, it updates its memory, it sends out some photons that go into the eyes of the user, that updates their brain state, then they type things, and then the key presses go back round to the computer. And so we've sort of closed off, we've taken these two open dynamical systems and kind of wired them together to close off the system in a way. And so we can visualize a lot of systems by wiring together these open dynamical systems like that. For example, it might, and we can visualize a lot of things. For example, it could also be that maybe instead of calling this type, let's call it something more general like readouts. So it might be that not only keys get pressed, but some other kind of action gets induced by this interaction that the user has with the computer. And so then this whole kind of composite system can be thought of as a sort of machine for producing actions, right? In a sense, at least in this model, it doesn't take in any inputs, but it produces actions. And then, you know, maybe we might also have the internet coming in over here and all sorts of things. It's very interesting kind of way of thinking when one starts thinking about how we can wire together these open dynamical systems. Now, I think that it's an idea that's sort of underappreciated. There's some really great work by David Spivak and David Jas Myers, among many other people, who've come up with some really amazing formalisms for a lot of this stuff. And they can allow us to talk about these open dynamical systems. There's ways to think about them related to lenses, which really let us make sense of things like these wiring diagrams. And I think that's really great. There's also David Spivak, among others, of sort of being really pioneering this idea of mode dependence open dynamical systems. So the idea there is that we have, as I've already said, but also the wiring patterns involved in these little communicating open dynamical systems might change based on their internal states. And I think this is a really cool idea. Like, you know, maybe eventually the user gets sleepy and they stop using the computer and they wire up to something else, like a bed or something. So, you know, the ways that things wire together can change based on their internal states. And there's a really great formalism for that I'm going to cover. Okay, so now we know about the general idea of these open dynamical systems. Let's connect them with this idea of lenses, because lenses give us a very powerful formalism for thinking about how to wire together different open dynamical systems and really let us connect to a lot of things. So we can picture the kind of lenses I'm talking about today like this. I think they're called bimorphic lenses. And you can think of this sort of picture as just encoding that we have these two maps here. So it's similar to before. When you see a picture like this, you can say, okay, that's some kind of graphical language. But when you really dig down into it, in a sense, all that matters is that we have these two functions here. So what we have is this map F sharp, which is sometimes called put, and that takes in something from A plus and something from B minus and gives us something from A minus. So there it is. It's a function like that. And we also have this other map F, which is sometimes called get. And together, these two maps form our lens. And so we write it like this. We say that F sharp paired with F can be considered to be an arrow from this object here, A minus A plus, to this object here, B minus B plus, within a so-called category of lenses. So let's write this down a little bit. So what we're really trying to do is define a category here that I could call lens set. So what that means is it's the category of bimorphic lenses, and we're imagining it being built on sets, meaning that we're thinking of these things as being sets. Actually, we could do a similar job for any Cartesian category, any category with products and terminal objects, but we might as well work in sets. It's easy to think about, and this is sort of related to how we normally think about open dynamical systems and so on. So you can see by looking at these, so you can see by looking at these functions here that in a way a lens can be thought of as a kind of generalization of the Moore machines or open dynamical systems we were talking about before. So in particular, we can consider the sort of special case where we've got the A plus equals A minus equals our set of internal states. And then if you look at the form of these kind of maps in that case, well, the put map is like a update map and the get map is like a readout. So the punchline here really is that our open dynamical system is really a lens from SS to B minus B plus. So we could write such a thing as F sharp F. And then this would be the update function, and this would be the readout function. So we can see now that lenses are really generalizing the idea of these open dynamical systems. And this is very cool, basically because we might have some more general kind of lens, like say something that goes from B minus B plus to C minus C plus. And then if we sort of post-compose that with this other lens here, then this composition is itself going to be some kind of open dynamical system, but somehow we've messed about with the interface, with the sort of wiring of it. We're going to be a lot more explicit about this shortly. But basically, thinking of these open dynamical systems as lenses lets us compose open dynamical systems together to form bigger open dynamical systems. And it really kind of breathes life into this, and it really kind of makes this graphical language make sense here. So speaking of this graphical language, let's go back to this picture here. So I was saying that this picture is a sort of way of depicting this lens here. And this lens here is an arrow from this object here to this object here in this category of lenses. Now, I don't blame you for not understanding what I mean by category of lenses because I haven't defined it properly yet. So far, I've just told you that the objects are these pairs of sets, and the arrows are pairs of functions with this kind of form. I haven't told you what the identity is, and I haven't told you how to compose lenses. So I'll tell you that shortly, but let me just address a sort of mystery here. So I'm saying that this sort of picture is a picture of this kind of lens here. So, okay, if you look at this picture, you can see, well, all right, there's this F sharp here, which is taking in A plus and a B minus and spitting out an A minus. So that's there. And there's also this F here, which is taking in A plus and spitting out a B plus, so that's there. You could say, okay, I can see that the forms of these functions are sort of encoded in this picture, but there's obviously more going on in this picture, right? There's there's some kind of copying, there's some kind of feedback loop, and most mysteriously, there's this kind of thing. What is this? It's actually supposed to be a hole, right? So I've just drawn this like hatched oval thing, and somehow I'm saying this should be like a hole. So why am I drawing a hole in the middle of my diagram? Well, the interesting thing here is how you compose lenses. So the thing that's going on here is pretty interesting. This F sharp F is an arrow that goes from A minus A plus to B minus B plus. So you draw it like that. But now what happens if we want to pre-compose it with something else? Well, let's say we have some lens H that comes from some other object. How could we draw that? I draw a H. There we are. So it turns out that actually the way that we depict this, or the way that we can think of it, is by drawing a picture of the lens H inside this hole. So this is very interesting. It turns out that pre-composing a lens can be sort of visualized by drawing that lens inside the picture. And similarly, if we post-compose by some lens Q, then we'd be getting Q, we'd be getting the hole in the picture of that, and we'd be sticking this lens inside that hole. Actually, let me just show you a visualization of that latter. Actually, I'm going to call this thing we're post-composing with G. So here's the idea. So here's the idea. We've got our lens G. So this, we could write it more properly as G sharp G. And, you know, we can draw that as an arrow. So G is this arrow from B minus B plus to C minus C plus. And then what we want to do is we want to compose G. So G, we want to compose capital G after capital F. So if we look at the picture of capital G, just in a similar way as before, it looks like this. And we've got to draw a sort of hole here. And now, if you look at the hole, before the hole we have B minus, and after the hole we have B plus. And now if you take a look at F, you see that it has just the right form to fit inside this hole. So how do we compose, how do we compute this composition here? Well, all we do, sort of visually, is we just take this picture of F and we stick it inside this hole. And when we do that, if we sort of just draw it out, it ends up looking like this. So here's where we do make use a bit of our sort of graphical language. We, in some sense, we can imagine at least some of this stuff, apart from the feedback loops, are happening in set, right? So we can copy things. And, you know, if we slide this F to the right, past the copy, then two Fs are going to appear, and then we can like slide this F back around here. So basically, if you rearrange the picture a bit, you can essentially rearrange it to look like this. And you can kind of convince yourself that in some sense, like if I said to you, I want to compose G and F, and I want the result to have this similar sort of form, that there's like some kind of a put map and then a get map, I think this is what you'd end up coming up with. And this is the way that you compose. So the sort of punchline here is that the composition of these two lenses, we can write like this, U, G, F. So the composition, again, is a lens. I'm saying that this triangle commutes. I'm saying that composition of these babies is this one. Now, the composition of two lenses should be a lens. Its get map or readout map, however you want to think of it, is pretty easy to get. You just compose the get maps from the original lenses. So this part is easy. This is just G after F. The put map is more interesting. Basically, it involves doing some sort of copying and using the put map of G in the put map of F. You can just read this like a wiring diagram in the monoidal category set, if you like. I've also written out what U is in more traditional notation here. But yeah, that's basically how you compose lenses. So what I'm saying here is that these bimorphic lenses form a category, and the identity arrow looks like this. So now I've told you the necessary information, we can speak about the category of lenses, in this case on set. And like I say, I think these things are called bimorphic lenses. The terminology around lenses I find quite confusing because there's many different kinds. But yeah, I think these ones are called bimorphic lenses. So these are really useful for studying open dynamical systems. Like we've already seen, open dynamical systems are special kinds of lenses. They're the kind that have this sort of form. And this is what we've been talking about so far. But also lenses let us compose these systems together. So the key idea here, and this is a very interesting idea, is that actually the wiring diagrams themselves are also lenses. So they're also examples of these bimorphic lenses. So I'm going to go over this now. I must admit, I think that this is maybe something that might be a bit hard to pass on a first viewing. So don't worry if you don't get this next bit. It's I think just having an intuitive notion of how the wiring diagrams work will be fine, and I'm not going to build on this much. But it is cool if you can get your head around it, because then you know how to compose open dynamical systems in a general sort of way. So firstly, actually, the first bit is easy to understand, which is a sort of certain structure, a certain kind of thing that we can do to lenses. So that's easy to understand. So I've now introduced this category of bimorphic lenses. It turns out that it's a monoidal category. So it turns out that we can take the product of a pair of objects in this category, and that's easy to do. So let's say we have A1 minus A1 plus, so that's a pair of sets, that forms an object. Let's say we have another object. Now I'm saying that we can take the monoidal product of these two things. And the way that you do it is totally simple. We just take the Cartesian product of the sets upstairs, and we take the Cartesian product of the sets downstairs. So taking the product of two objects is easy. Taking the product of two arrows or lenses is similarly really quite easy. So pictorially, say we have like a lens like this and a lens like this, and we want to compose them together. Essentially, we just put them pictorially parallel to each other. That's pretty much all we have to do. Basically, you just draw the pictures one on top of the other. Slightly more involved as shown here, but basically the idea is that you know, we've got our lens number one and lens number two, and we're sort of just picturing one on top of the other. So the get map is just F1 times F2 in the sense of you know, taking the product of two arrows in sets. It's just like applying the two functions in parallel. The only slight complication is that, you know, our sort of thing that we're feeding back is A1 plus times A2 plus, and then we're sort of copying that and we're feeding a copy of it back. So what's coming in here is A1 plus times A2 plus times B1 minus times B2 minus. But to use our get maps for system one, but to use our sort of get maps for lens one and lens two, we've just got to sort of swap around these two inputs here. So we've got to do a little bit of permutation of the inputs of this sort of composite get map. But it's pretty self-explanatory. And then this H and this H sharp are going to be forming the sort of monoidal product of these two lenses. So basically, it's pretty simple. To take the monoidal product of two lenses, just stick the pictures of them one on top of the other. That's the sort of top and bottom of it. And so this is all very nice because it turns out now that this category of lenses is a monoidal category, right? We know how to take the products of the objects and the arrows. The monoidal unit is just this lens with singleton set, and it's pretty simple. The lovely thing now, though, now we know how to compose lenses. The lovely thing now, though, is now we know how to compose lenses sequentially, and we know how to take the sort of product, or we know how to do lenses in parallel. We can now speak about how to compose lenses more generally, and this gets very, very interesting. It's a very powerful sort of framework. So, okay, wiring diagrams are pretty cool because they allow us to describe wiring patterns, and they allow us to compose together open dynamical systems. So in a moment, I'm going to explain how we can think of a wiring diagram as a lens. Before I do that, let me just show you the kind of end game. So you see, I'm going to do it with an example because it's the kind of thing that's kind of really easy to show people, well, fairly easy to show people with an example, but the general description is kind of clunky, at least without applying too much abstraction. So basically, the idea is that we have a wiring diagram like this. You can see that we've got this sort of outer box, and then we've got these inner boxes. And so I'll speak about things like inner outputs, by which I mean outputs of an inner box. So we have inner outputs, inner inputs, outer inputs, and outer outputs. So these are these different sorts of places where wires connect to boxes. See that our wires are labeled with objects. We could think of those as sets, or we can work in a more general abstract level, but let's think of them as sets. Now, you can think of a wiring diagram, as I say, as just being a wiring diagram itself. And there's a way of composing wiring diagrams with each other because wiring diagrams are lenses. So you can imagine filling this box here with more wiring diagrams, and that's like lens composition. I was explaining how we can fill those holes with other pictures, and it's kind of like that. I know that's very vague. I'll say something more definite very shortly. But really what we want to do with these wiring diagrams is use them to compose dynamical systems. So the idea is something like this. Imagine putting an open dynamical system inside each of these boxes, and then that's going to make the whole thing into a big open dynamical system. So that's the sense in which wiring diagrams allow us to compose. And honestly, the next bit, I think it's quite a lot for the first viewing. So don't worry if you don't understand it, because I'm not going to build much on it, but let me show you how to do it. So basically, what we want to do is stuff like, if I zoom in here, you see I'm putting a little open dynamical system inside this box here. So I'm calling it F2. Similarly, I want to put an F3 in here and an F1 over here. So I want to load open dynamical systems onto each of these boxes and then get the whole thing itself is going to be a big open dynamical system. So if we sort of zoom in here, we see that really this open dynamical system, as usual, it consists of these two maps, right? We've got this F2 sharp, which takes in a B, and S2 and spits out an S2. So here S2 is the set of states of this second dynamical system. And then F is the readout map, sending states to values in the set C. So this F2 is really described by this pair of maps like this. And we imagine that we've similarly got, and similarly we can imagine we've got F1 sharp F1 describing this open dynamical system, and another lens describing this open dynamical system. And then basically, yeah, we want to compose them. So to do this, the approach is basically like this. Somehow, the wiring diagram itself is going to be described by this lens. And I haven't explained how this works yet. I'll do so momentarily. But what I'm saying is that this lens, W sharp W, somehow describes this wiring pattern in a very general way. And then the idea is that we can also describe our individual open dynamical systems, capital F1, capital F2, and capital F3. We can monoidal product those together, and then we can compose with our lens representing our wiring diagram. And it's kind of magical that this composition here is going to end up actually giving us this sort of open dynamical system that's like this kind of composite, where we have these little open dynamical systems and they're sort of wired together and interacting. So this is really how we can compose open dynamical systems. Now, honestly, if you just draw the diagrams, you can, I would say, if you think about it for a bit, you can probably figure out how you should compose the open dynamical systems anyway, but it's lovely that this is a formalism for it. So the missing bit then is I need to sort of say how we construct this lens here that corresponds to this wiring diagram. And this is the bit that's a bit difficult to convey, but I'll try. So here's the idea. I'm going to work through this particular example. So let's just think about this example for a start. This is a wiring diagram. You see that the outer input here is A, and I'm drawing that here. And the outer output is C, which is here and here. And just like in the pictures before, when we have a lens, it's this thing on the right here, which is really giving us the sort of stuff on the outside, and the thing on the left is the stuff on the inside. So what we've got here, this object here, is really representing the inner inputs. So if we have a look at all these little boxes, these inner boxes, and we just Cartesian product together all the different inputs, we've got A times B times B. And so these are the different inner inputs. And so if you like, a member of this set is a sort of tuple, which is describing all of the inputs that the different inner boxes in our system get. And, you know, if you imagine the thing running at any particular time, you could sort of take a snapshot and look at, you know, this tuple of the inputs. Also, this down here is going to be the inner outputs. So we've got B times C times A. Okay, and now it's actually, I can say it very succinctly, a wiring diagram is nothing more than a general lens from this object here to this object here, which means that it consists of a function W of this sort of form and a function W sharp of this sort of form. which you can get just by, looking at the standard sort of way that lenses are described. The only caveat is that these functions here are only made using projections and pairing. In other words, these have to be functions that we are making just using the kind of Cartesian structure of sets, or the Cartesian structure of our category. That means we're allowed to send things to terminal objects, we're allowed to do projections, and we're allowed to pair maps, and we're allowed to do any combinations of those things. So we can commute things, we can copy things, we can discard things, but we're not allowed to do anything else. We can't do any like custom functions like timesing something by 2 or something. To put it more, to say it more abstractly, I could say that, these arrows W and W sharp have to be made using the sort of free Cartesian structure, which you get using the objects corresponding to the wires. But in this case, but anyway, that's all a bit abstract. What's really going on here? Well, what's really going on is, to describe a wiring diagram like this, we really have to say 2 things. We have to say, if we look at the outer outputs, there's going to be a certain number of wires which are poking out of the right-hand side. There are outer outputs. And we need to say how they are connected up to other stuff inside. So what we really want to do is specify a function, a type of wire type preserving function, from the outer outputs to the inner outputs. So in this case, we're sending this outer output C to this inner output. So you could think of that as a function going sort of this way. So you could think of that as a function, but that would be going the wrong way. But actually, you can encode that as a projection going this way. I know that's a bit cryptic, but I'm trying to say that. But I'm trying to say that this, well, in this case, we didn't even really have a choice. We sort of had to do this second projection here to get this C. But what I'm saying is that more generally, when you're sort of using pairing and projections to form a function from the inner outputs to the outer outputs, you could sort of equivalently describe that as saying, well, for each of my outer outputs, I need to sort of point out which inner output ended up getting connected to that. And you could do that as a function going the other way around. And then you can encode you can encode that function in terms of projections and pairing, and then you've got your sort of get map or your readout map or your W. And then the other part of the wiring diagram is this W sharp. And again, you can say, well, really what that is it's going to be this function which is made out of projections and pairing, and you're going to be sending the product of your inner outputs and your outer inputs to your inner inputs. Again, I prefer to think of it the other way around sometimes and really say that what we really want to do is for each of our inner inputs, so for each of these babies, we need to sort of map that to either a inner output, like that, for example, or an outer input, like we send that one over there, for example. And so doing a sort of type preserving function like that, that would really be a function from like this set of 4 things over here to this set of 4 things over here that preserves types. But then you can kind of turn it backwards and encode it in terms of projections and pairing. Anyway, in this case, you can see that having a W sharp that ends up like this is really describing what's going on. And like I say, you can think about this in a pair of ways. You could think of it as for each of these inner inputs, like each of these 4 things, you're really mapping it to something over here. So you're mapping each inner input to an inner output or an outer input in a sort of type preserving way. Or you can just literally think of this in terms of projections and pairing and so on, in which case you're sort of reading this wiring diagram going this way. Anyway, maybe that's not so clear. Maybe it takes a bit of time to think about it, or maybe we can just carry on, because the kind of graphical calculus of these open dynamical systems, I would say it's sort of intuitive pictorially. Anyway, that's how you describe wiring diagrams. What do you do with them? Well, let's say we want to put these systems in here. So, for example, this second dynamical system that we want to put in here is going to be described by something that, okay, it's outer inputs. Okay, so its set of states is S2, S2, and its outer inputs are B, and its outer outputs are C. So that's going to be described by an arrow like that in the category of lenses, for example. And similarly, we're going to have an open dynamical system for this and this. And then all we do is we take those and we tensor product those together. And the way that you can visualize that, if you like, is sort of imagine drawing these three sort of boxes with their sort of innards, which describe the open dynamical systems, and drawing them in parallel. And so that would be like what this arrow looks like, which is really an open dynamical system, because this evaluates to S1 times S2 times S3, S1 times S2 times S3. So this arrow here has this normal sort of form that open dynamical systems should have, that, you know, like the pair of objects in the source are both the same, they're both like internal states. So this is an open dynamical system. And then when we compose it with our wiring diagram, the whole thing also has this sort of form of an open dynamical system. And what it really represents is the open dynamical system you get by loading a little open dynamical system into each of these boxes. And it's a really nice formalism, because it lets you really like easily relate, potentially very complicated patterns of interaction in terms of these things. I mean, in my old job, I was doing mathematical modeling of marine ecosystems using partial differential equations. This was one of my old jobs. And I wish I'd known about this back then, because there's different, I learned about this through David Jasmeyer's book mostly. And he describes how this same kind of lens formalism, like I've been talking about it in terms of discrete dynamical systems, just functions, just working in sets, because that's easy to think about. But there's also a version which is probabilistic, using open Markov processes. There's also a version that uses continuous things. So you can have like ODEs and things running on these things. And that would have been so useful for what I was doing, because it can get so intricate when you're doing kind of modeling of complex systems, to keep track of, you know, the difference between like how things are wired together versus this sort of internal dynamics. And this gives a really lovely sort of way to organize all that. And there's lots of connections with more abstract maths that I'm trying not to mention, because I'm trying to keep this as simple as possible. But the sort of long story short, we can wire together little open dynamical systems to make big ones, and the result would look something like this. And notice that now a state of it is like a triple of internal states of the little boxes. which makes sense, right? Because to know how a population is going to behave, you'd want to model the states of minds of each of the people in the population if you want to do it exactly. Okay, so open dynamical systems, as I've already explained, are a pretty meta idea. Like it's pretty amazing to be able to wire together these different Moore machines to make more elaborate Moore machines, and we can already use it to model all sorts of things to do with computation and biology and engineering and so on. Now, it turns out, though, we can actually go a lot further. So there's a recent idea, which is this idea of mode-dependent dynamical systems. Now, I know mostly that Spivak has been doing a lot of work with this. I'm sure a lot of other people have too. And so I want to introduce the idea. Now, there's a good thing here because there's a couple of different ways that we can look at this. So I've mostly been talking about this category of bimorphic lenses so far. This one where we have these objects as these sort of pairs of sets and then the morphisms of these lenses. But these lenses are relatively simple, and there are more elaborate kinds of lenses called dependent lenses. So I've actually already introduced the category of dependent lenses. It's what I build to in my video on vibrations. So like really close to the end of that, I describe what this category of dependent lenses is. Now, looking at it in terms of vibrations is one way. I think a much nicer way to look at it is to say that it's the category of polynomial functors. So I'm going to introduce this. Now, this category poly is something very magical. I mean, it's an equivalent way to look at the category of dependent lenses in some sense, but thinking of it in terms of polynomial functors is very beneficial. It's a little bit weird when you start looking at it, but once you get used to the formalism, you realize that it really makes it possible to think about all sorts of interesting things to do with interaction in a very kind of natural way. So it turns out that the category of polynomial functors, what these basically are endofunctors of sets, so a functor from sets to itself, which have the form of a polynomial, right? So, for example, we could consider the functor y plus y. So y here is a variable, basically. So if we operate this functor y plus y on a set S, then the result would be the coproduct of the set S with itself. Actually, there's a bit of a different way to think about these polynomial functors, a bit more of a sophisticated way, I suppose. And that's firstly to consider the Hom functor. So so let me introduce these polynomial functors a bit more systematically. So firstly, let's say we pick any set we like, A. And now we can consider a functor that we're going to call y to the power of A. Now you can think of y as a variable, but it's cleaner and better to think of y to the power of A as Hom of A comma blank. Or I could also write it as a set of A comma blank. So this is an endofunctor of sets. So if we operate this endofunctor on a set S, then the result is going to be what we could write as set A comma S. Or we could also write it as S to the power of A. And we could say this is the set of functions from the set A to the set S. How many such functions will there be? Well, there's going to be this many functions. So the number of elements in S to the power of the number of elements in A. So this is good notation. But notice that what we're really doing here is we're applying this endofunctor here to the input S. Okay, and really when we do that, we replace this variable y with the S, and that gives us the result. So this here is what we could call a representable functor. That's just what you call these functors of the form hom of a comma blank. And so what a polynomial functor is just something that we can form as the coproduct of representable functors. So, for example, we could consider y to the power of 2 plus y to the power of 2 plus y to the power of 3. Now, when I write numbers like this, for example, when I write a 3, that's really shorthand for the set that has 3 elements. So this isn't a number, this is a set with 2 elements, and so on. Now, the way coproducts work is the way you'd expect them to work when you're working with polynomials at school and so on. And so, you know, we could also write this as 2y squared plus y cubed. And then if we wanted to expand this out, let me really expand it out unnecessarily in unnecessary levels of detail. This is really a set of 2 elements producted with this hom functor, hom 1, 2, comma blank, co-producted with hom 1, 2, 3, comma blank. And so that is equal to that. So hopefully that clarifies what polynomial functors are. Still the question remains, what is poly? So poly is a category, and it's a subcategory of the category of endofunctors of set. So we write this to denote the category of endofunctors of set. It has objects as functors from set to set, and it has arrows as natural transformations between them. And so what we do is we take this category of endofunctors, and then we just take the full subcategory on the polynomial functors. We only look at the objects that have this polynomial form, and we keep all the arrows between them, all the natural transformations. So that's what poly is. It has objects as polynomial functors and arrows as any natural transformations. So that's basically it. That's what poly is. So we could write a sort of general object of poly like this. So this would be a general object P, and we can write it in this kind of form. So we'll have some set I, and then if we sort of co-product over the elements in I of y raised to some power, then that's going to describe our polynomial. So here I'm writing pi using square brackets to denote one of these sort of exponents. So really, this y to the power of pi, we could write it like this: hom of pi comma blank, or sets pi comma blank. So this is just a sort of general set, but I'm referring to it with this funny kind of notation. And so what this is just a sort of coproduct of endofunctors that look like that. And also, this is kind of fun notation. This set of indices here, we can also write that as P of 1, where notice I'm writing the 1 here with round brackets. So this is a bit different. What I mean when I use round brackets is I mean that I am applying this polynomial functor to this input here, which is a singleton set. So round brackets means applying an endofunctor to a given input. Square brackets means referring to the exponents within the endofunctor, within the polynomial functor when it's written in this form. So okay, that's a lot of bookkeeping and all the rest of it. And at this point, you might be saying, well, okay, you've got all these sophisticated ways of talking about polynomial functors, but but what are they? What are we doing with them? Um, and this is a funny one, because we're not usually that interested in actually applying these polynomial functors to things. And this is a bit unusual. Usually in category theory, when you are talking about functors, you're mostly interested in how these functors work on things, right? Like how do they map objects? How do they map arrows? But at least for us, with our applications of poly, we are more interested in the arrows between polynomial functors, because when you have two polynomial functors, you can kind of look at the sort of combinatorial structure of those polynomials in some sense, and that really tells you about these different kinds of so-called dependent lenses that you can form. And these dependent lenses really they generalize the ordinary kind of bimorphic lenses that I've been talking about so far. So that again, it might sound a bit cryptic. I think everything is going to become clear if we just have a look at an example. So here are two polynomial functors. So these are two different objects of poly. And now we're going to ask a very simple question. What is an arrow from this polynomial functor here to this polynomial functor here? This is the question we're going to ask. And the answer is going to be that it's going to be a dependent lens. I haven't said what that is in this video, but we're going to look at things in a certain way, and hopefully this is going to become clear. And then, like, the main reason that polynomial functors are awesome for thinking about mode-dependent dynamical systems is going to become clear. So, what is an arrow in poly from this dynamical system here to... So what is an arrow in poly from this polynomial functor here to this polynomial functor here? What is this? Well, there's a short answer, which is not really very informative, but it is very true. And that answer is a natural transformation, right? Like, this is a functor from set to set. This is a functor from set to set. And so a morphism alpha from this to this is just a general natural transformation from this functor here to this functor here. And we can work with that, right? We know the definition of a natural transformation, and we can work with that. But it turns out that just answering it directly like that is not as helpful as it could be. There's another way to think about what a morphism from this to this is, which is far more beneficial for us. And I'm going to describe that now. Basically, you get at this useful second perspective by using the Yoneda lemma, because, like, this is just a coproduct of representable functors. So an arrow alpha from or a natural transformation alpha from here to here, you could write it as a sort of co-pairing where, you know, for example, alpha 1, where, you know, well, like alpha 1 has this kind of form, and alpha 2 has this kind of form, and then this baby is Hom of 3 comma blank, and so we're interested in a natural transformation from this Hom functor into this, so we can apply the Yoneda lemma, yada yada. That kind of thought gets you to the this alternative form that I'm about to describe, which really is the key, I think, to using polynomial functors for this dynamical system stuff. So um, you don't need to think about the Yoni dilemma for this, but you can use it to verify what I say. But I'm just going to tell you directly. So, okay, let's ask again. What is a general arrow from this polynomial functor here to this polynomial functor here? Well, firstly, how can we think of this polynomial functor here? And I've drawn this kind of graphical language for it underneath. So what are we doing here? Well, let's call this polynomial functor here P. And so we can ask a question, which is, what is P of 1? Well, if we plug a 1 in for the y, then we're going to get this, this is going to become 1 plus 1, right? Or a set of two elements. So this here is P of 1. Maybe I'll write it in blue. So this equals P of 1. And if you like, if you wrote this polynomial as like a sum of representable functors, this would be how many things you're adding together. There's another piece of terminology which Spivak uses to talk about these things. He would say that P of 1 is the set of positions. So he uses this very colorful language to say that these are positions, and if we have a particular position, then there's going to be a set of directions over that position. And that set of directions corresponds to the exponent of the corresponding representable functor. So, okay, that sounds too complicated. Basically, the idea is like this. You have, okay, maybe I'll do another example just to sort of hammer this home. So you have any sort of polynomial you like. So for example, y squared plus y squared plus y cubed, and then let's say this is the polynomial r. And then you look at r of 1, that's basically like how many of these powered up y's are you adding together, and that's going to be our set of, and that's going to be our set of positions. And then above every position, there's a set of directions that corresponds to this power. So this first position has 2 directions over it. This second position has 2 directions over it. And this third position has 3 directions over it. And so we can represent the polynomial functor R with a picture like this. It's like a kind of way of representing a function using fibers, if you like. So this is really interesting because it kind of gives you a way to think about a polynomial functor as basically like a set of different positions, and then in each of these positions you have different directions. So think about, for example, you can move around, and then wherever you move around, there are different directions that you can see in, or sort of look in some sense, or maybe like different sorts of sensory data are available to you. It's a bit fuzzy, but you can kind of think about things in those kind of ways. Okay, so that's just a way of drawing pictures that correspond to these polynomial functors. Let's go back to our original question. What is a morphism? What is a natural transformation from this polynomial functor to this polynomial functor? Well, here's how we should think of it. This is what I've been building up to. Firstly, we want to send the let's call this polynomial functor Q. Now, firstly, we want to do a function from the positions of P to this set of positions of Q. So we can just pick any function we like. I'm going to pick a nice easy one. And we're going to call this function f. So we're mapping the positions of P to the positions of Q. That's the first part of information that we need. The other part of information is like this. For every position of P, we look at where the second part of the information is like this. For every position of P, we look at where that position gets mapped under this sort of forwards map F, so it gets mapped to here. Then we look at the directions over that in Q. And we map each of those directions up here to a direction which is over where we started. So if we say this is 1 and this is 2, then this here is going to be f of 2, and this set up here is going to be q of f of 2, and we have to map each of these directions here to some direction that was over the 2 that we started with. So we could call this map f sharp subscript 2 because it's sort of related to this. And we have to do this for every element in our original set of positions of P. So also we have to look at this, and then we say, oh, it goes here. And so we have to map this direction here to one of the directions over where we started. So we have to specify this other function, f sharp 1. And that's it, we're done. So in one of Spivik's videos, he describes a really nice way of thinking about this, which has to do with abstracting problems. So think about P and Q as different problems. And imagine that there's a way to translate problems of type P into problems of type Q. Like you have this kind of thing happening in computer science, for example. You like, oh, well, if I can solve these problems of type Q, then I can translate my problem of type P to that. And think about how that works, right? When you can do that, what you want to do is you want to firstly be able to send problems of type P to problems of type Q. In other words, you want to be able to map positions of P to positions of Q. And then when you have a position of Q that you've landed on, or a problem of type Q, if you look at the directions over that, or the solutions to that problem in that instance, then you want to be able to map those solutions back over the solutions of the thing that you started with. And so we have this sort of two-way thing. So that's basically the idea. I've spelled it out a bit more concisely and in general here. So we'll suppose that we have a couple of general polynomial functors. So, for example, we can write Q like this. We sum over the. So, for example, we can write P like this. We're adding over the members of P of 1. That's the set of positions of P of y to the power of P I in square brackets. And we can write Q in a similar way. And then we ask what's a general arrow from P to Q. And it's a natural transformation, but we can sort of write it in this corresponding form. That's the way we like to think of it. And so what we're really doing here is we've got this sort of forwards map, sending the positions of P to the positions of Q, but also for every position of P, if we look at where that position lands under our forwards map, and we look at the set of directions over it, we need to specify a function from that set of directions back to the set of directions above where we started in P. So that's exactly what a morphism in Poly looks like. And this is really interesting because basically, if you think about it now, you can kind of see why this is called a dependent lens. I mean, it takes a bit of thought, but imagine a picture like this, where each of these fibers has the same number of elements on both sides. So in that case, what we'd be talking about is we'd be talking about so-called monomials, right? Like polynomials that have this special form that, yeah, we're adding together a load of exponentiated y's, but each of those y's has the same exponent. So the thing ends up just having this form, and it's a monomial. And it turns out that when we're thinking about a morphism between monomials, we're basically looking at a picture like this, where all of the fibers on the left have the same height as each other, and all of the fibers on the right have the same height as each other. And that turns out to exactly correspond to the bimorphic lens story that we've been talking about before. So basically, what I've been trying to say in a nutshell is this picture here. I haven't really explained why. I haven't really explained what dependent lenses are or why they correspond to polynomial functors. I'm not going to do that. But what I have been trying to say is that we know what poly is. Now we know what these monomials are. They're just these simple kinds of polynomials. And I'm saying if we look at the full subcategory of poly on the monomials, it looks just like our category of lenses that we started with. And this is really neat. So let's just take a closer look. So yeah, this is what I'm saying. But let's just take a closer look at how this works. So here are a couple of monomials. For example, this one on the left here, we could write it as 3y squared, and this would be 2y squared. Now, let's just ask what's a general kind of arrow in poly from here to here. And hopefully we're going to see that it ends up looking like one of these bimorphic lenses. So how do we describe it? Let's follow our rules. So firstly, we have to give a function, say that one, f, that goes from a plus to b plus. Okay, so far so good. That's one of the things that we had when we considered a morphism like that in the category of lenses. The other thing we have to do, following our rules of poly, is that for every position, in A, we have to give this map f hash subscript I that's going to go from the set of directions over where that position gets sent to. Well, we know that each of those set of directions is going to be b minus, and we have to give this map that goes back to the set of directions above where we started, which we know is a minus. So what do we have here? Well, what we really have is that for every I in A plus, we're going to have a map from B minus to A minus. So if we just sort of collect all these maps together, we can collect them together to make a big kind of function like this. Right, where f hash I comma blank is this baby here. So look, that's this. And so you can see that in this special case where all these fibers have the same height, a morphism in poly between these polynomials, it just corresponds exactly to this kind of bimorphic lens thing that we're already talking about. So, that's the basic idea. Okay, so what have we got out of this then? Well, what we've really done is we started here, and then now I'm claiming that there's this sort of equivalence between these two different things. And so, in a sense, what we could say is we've sort of generalized. We could draw it like that, right? We've sort of generalized our category of bimorphic lenses to this category of polynomial functors. What does that give us? Well, what it gives us is the ability to think about mode dependence. Now, I don't want to make a video that goes on for absolutely ages, so I'm going to be brief now, but basically what we get out of it is like this. So far, the main thrust of what we've been doing is to say that if we consider, okay, I'll write it in the lens way first. So the main thrust of what we've been doing is to say that if we consider a lens of this form, then it's an open dynamical system, or it's a Moore machine. They're equivalent as far as I'm talking today, at least. Although actually by open dynamical system, aficionados mean something more general. But anyway, yeah, that's the main point of today, right? But now I've just been saying that actually we can write this in as an arrow in poly. So it would be an arrow like this. So that's a new way that we can refer to the same thing, an open dynamical system. But now what we can do is we can consider more general things. We can consider an arrow in poly of this kind of form. And what is this? Well, this is a mode-dependent dynamical system. Well, what does that mean? Well, let's imagine that we had different types of interaction patterns that we might have. So let's say, for example, we have a computer, and sometimes the computer is ready to accept input. So in that case, our set of inputs might be something interesting, but our set of outputs would just be a singleton set. Boring. We can't really, giving an output doesn't really give you any information because there's only one possible value, right? So we could draw a situation like that. It might have a set of internal states, and it might be able to do some interesting stuff out in here, but it can't really output anything. So that would be one possible mode our computer could be in. It could be in sort of listening mode. It could also be in this kind of mode where you can't give it any input, it can't produce any output, but it might be thinking something interesting. So in this case, our set of inputs and our set of outputs are both trivial. Or it might be in this kind of mode where the set of inputs is trivial and the set of outputs might be non-trivial. So here it's in kind of speaking mode. It can produce outputs. And now what we can do, if you think about what a morphism is in poly of like this, for example, one of the things that it involves is going to be this forwards map of this kind of form. And what that really does is it says, if you have the current state, that's like a position of this polynomial here. And depending on which position that gets mapped to under f, tells you which kind of mode your system is going to be in. And if you sort of unpack this and think about what these polynomial functors look like in general, just a general polynomial functor from here to here, you'll find that what you really have is like an open dynamical system, but where the sort of interface fashion, what the inputs are and what the outputs are, what sets they belong to. Are they like this or like this or like this? Well, that can be variable depending on the state. And I think this is a really beautiful idea because there are so many things in the world where things are going around and they're open and they can have inputs and outputs and change state, but also the way that they connect to things can change. And I think that this is super important. Like, imagine, think about your life, right? You wake up in the morning, um, you're sleepy, maybe you decide to wire up to some kind of coffee maker, and then you can get your coffee, and you have to put the coffee in, and then once you put the coffee in, you close the top of the coffee, and then the input to the coffee maker is closed, and then you press the button, and whatever. You can think of the whole lots and lots of interactions. For example, now you're watching this YouTube video, you're sort of wired up with your computer, and you're receiving these verbal messages, and it's altering the state of your brain. And then, maybe when you've finished this, you know, you decide to, your state of your brain's changed, and you decide to go for a walk or something, and then you're no longer wired up to your computer, and so on. It's a lovely framework for thinking about things. And so I've been using this for a while. I've been reluctant to make a video about these open dynamical systems because I've only learned about them recently, and there's just so much amazing material out there by David Spivak and David Jasmyers and other people explaining about this stuff in more detail. But I'm really blown away by the potential I think this kind of stuff has, because if you think about software systems, you can break them down into these little open dynamical systems in many cases, in a very kind of intuitive way, right? Like, for example, if you have like a while loop, the system's probably in thinking mode until it reaches some absorbing state, and then it can output something. So if you have some kind of big system that you want to describe, this is a great language for breaking it down. But also, nowadays, so many of our programs are connected to each other over the internet and so on, and they can act in different ways. And now we're starting to have all sorts of systems talking to each other over the internet. We have bots, and we have people connecting to things, and people playing online games and trading and doing all sorts of things. And I think that this mode dependent open dynamical system sort of language really could be actually the language to use to describe all of these things. Like, I wonder if, in the far future, our whole operating systems might just be like open, all made out of open dynamical systems. And we can probably use these things to formalize all sorts of interactions that we have, like economically or personally. If you're reading your emails and you're responding to people, we can maybe formalize a lot of that using these things. And I think if people make the kind of architecture to be able to, put the things that we're already doing into this framework where they do fit, it could really help us to formalize a lot of the things that are happening over our computer networks at the moment, which are in this very kind of, they're all written in different languages. So I was thinking about this, and it's moving towards this kind of idea of really being able to describe lifelike systems. I would say, because you can have universal Turing machines that can have mode dependent things. Your computer decides to connect to the internet, or you can have learning in there, all sorts of stuff. But I was wondering if one could kind of give this thing a little bit of a push to put some self-replication in there, right? So at the moment. So now we're moving into stuff that mostly me and my friend Jos Hoebe have been talking about, and it's kind of at a stage now where we're informally talking about this stuff. It looks like it could be a really interesting kind of research direction. Neither of us have that much time to actually push this thing forwards. If other people like the idea and want to push this thing forwards, please, you know, you can get in touch, or if you end up writing something, it might be nice if you could mention this, YouTube video or whatever, because I haven't published anything on this formally. Or maybe it's just a red herring, or it's already been done, or whatever. But the idea is like this. What if we have these open dynamical systems, but the idea is like this. What if we have one of these open dynamical systems? So, for example, something like this. Well, what about if the set of positions in one of the cases, but what about if the set of positions in one of the cases look like this? So, what is this? Well, this is the set of pairs of a function of this form and a function of this form. What is that? Well, it's another open dynamical system. So what I'm talking about here basically is the idea that we could have open dynamical systems with a sort of mode dependent dynamics. So sometimes they can rewire, but what they can also do is they can output other open dynamical systems in much the same way as us humans can decide who we want to talk to and so on, and how we want to move around and what we want to connect to. But under certain cases, we can also reproduce, like we can also have offspring, which are other humans. And then they can grow up and they can decide to wire to things. And basically, we're wondering if you can model such a thing by having open dynamical systems where the kind of readout is like something involving higher order functions. So in this case, the output of this is a bimorphic lens. It's fairly easy to have a case where the output could be a more general polynomial functor. And so we're wondering, what's the best way to do this? The motivation, like one of the motivations, is to talk about things in biology, right? So we have these organisms that can decide what they interact with in the world, but then they can also reproduce in certain cases. Now, exactly how you get self-replication out of this framework is something that we haven't worked out yet. Like the Y Combinator in computer science can give you something like self-replication, but it's not so straight. At least we haven't thought yet how you could put such a thing into this kind of framework, where we're more using a kind of Cartesian closed structure. So I think, you could work in Poly to talk about these kind of ideas. You could also more generally work in a category of dependent lenses over some complete Cartesian closed category, I suppose. So maybe then, you can connect with your lambda calculus and that. But anyway, the thing is, or the sort of question that we want to know is, what is a good formalism for having not only this case where we have these boxes slash open dynamical systems that can rewire, but also that we can allow them to reproduce. And it seems like something like this at a very naive level can already do quite a lot, right? You could imagine modeling a situation where you have like a man and a woman, and they're these boxes, and in a certain situation, their internal states make them wish to wire together, and then they exchange things, and then the woman outputs another kind of baby box, which originally is wired up to her by like an umbilical connection, but then eventually the baby can go out and grow up and interact with other things. And it seems like this could be a nice framework to look at this stuff. And maybe also then one can think about stuff like DNA and all sorts of things. But this is only a very recent idea, and maybe these ideas are not as under closer inspection they don't work out as well as matching my excitement about them. But I do think it seems like a very fun thing to think about. Also, this category of polynomial functors itself has some very beautiful structure. And also, this category of polynomial functors itself has some very beautiful structure, which can potentially make this sort of modeling project a lot easier. Again, it's something that like we haven't explored enough, but the point is this: imagine we have polynomial functors P and Q. Just think about actual polynomials like from school. If you times them together, then what you get is going to be something like this. So I'll delete that because these are not equal. So this, what I've drawn here is like a formula, the normal formula for timesing together polynomials. Now, take this formula, and instead of adding these things together, what we do is we times them together. So we're doing the Cartesian product of sets. I should say that up here, usually when I write things next to each other like this, that's what I'm talking about, Cartesian products. Anyway, when we have this formula, which is a bit of a deviation from the norm, this defines this sort of, I think it's called the Dirichlet product of polynomial functors. And I think it's also similar to the O times I was talking about before, but kind of like the original O times I was talking about was for these sort of bimorphic lenses, and this is the same thing but defined on for more objects. So this gives us a monoidal structure on poly. This category poly, actually, it's a monoidal category in lots of interesting ways, and this is one way it is. And it turns out that actually this gives us a closed monoidal structure. So to say it in a fancy way, this is going to be a right adjoint to this, or we have this kind of currying style natural isomorphism. And so this kind of closed monoidal structure, it seems like it can allow us to talk about this kind of idea of these mode-dependent open dynamical systems that can output other mode-dependent open dynamical systems. So, for example, we could speak about things like this. And I'm going to leave it there. So, like I say, this is at the end, this is all sort of speculative ideas. There is definitely some stuff that needs thinking about to do with this. Like, I'm not even sure it's clear that we really can get proper self-replicating structure out of this. Like, do we reach some kind of roadblock? Because for some reason, with these kind of Cartesian closed categories, it's difficult to actually refer to morphisms that can output morphisms that have the same form as them. Is there a workaround involving some kind of fancy use of like the is there some kind of workaround involving some kind of fancy use of the mode dependence? Like, a mother cannot produce an exact copy of herself instantly, but she can produce a baby that grows up similar to herself if it interacts with the environment in the right way, and so on. So that's one question. Another important thing is that another important sort of question or thing to investigate is like the kind of the difference between like outputting a member of a set of functions. Another important thing is to look at the sort of difference between outputting a member of a set of functions and an actual arrow in poly, right? It's like one is like a sort of name of a open dynamical system. The other one is the open dynamical system. And there's something about kind of using this kind of evaluation map to turn one into the other. And is there some kind of physical interpretation of that? What's it mean to go from sort of DNA to organism or whatever?